Oh, and if you guys have a scientific calculator that you normally use, you guys can take that out. If you normally use Desmos Scientific Calculator, can you open up a tab that has Desmos Scientific Calculator? This will be, I mean, your tests and your quizzes all year long have been calculator based, but for sure this chapter, you'll need a calculator. So as you guys find all of that, if you have, I'm gonna have an order or a list of things that I'd like you guys to get done in a particular order. Like if you haven't seen the videos to take the notes on the first 2 pages, that's what you'll do first. Or sorry, not first, but after we're done with our notes, you're gonna have a large chunk of time, I think, to get your homework done and to like just do the test corrections if you want to work with your groups on that as well. But so page 1, the sample spaces, it's we're going to summarize it in one example, but I'd like you guys to watch this because it shows you guys the long way of coming up with all of the sample spaces and possible outcomes, being tables and tree diagrams, and then the shortcut way, which is through the fundamental counting principle. And you guys see at the top of the agenda, there's a meme like, oh, I think the fundamental counting principle will help with that. And it's the idea that it's the shortcut way of doing these problems. So if you scroll down to the bottom of page 2, there's a little blurb, and I'll just talk about what we're moving into next. Probability is one of those units. I'm not kidding. It's like at the district level. There's always talks about like, no, what doesn't Algebra 2 trig take it, or why doesn't Algebra 1 take it? And the state of California had split the topics up to where probability was just like a topic they threw into geometry. There's like one segment of it, which is Monday's lesson, that's geometric related, and everything else is just kind of like, it's just, you know, it's just included in here. That's why I say we sort of are just done with geometry. So it's like an additional unit. And when I looked at the standards from that the state of California requires, permutations and combinations, we had a larger focus on it last year, and then we didn't get to a bunch of the different topics like conditional probability, independent and versus mutually exclusive versus dependent events. And so what we decided to do, or what I decided to do instead this year, was focus less on permutations and combinations, which are you've seen before, and or most of you guys have, and it's a what is it called, like an optional topic for the state standards, whereas these other topics on probability are required. So I'm going to cover the required stuff and just touch a little bit on permutations and combinations today. This file is where, you guys, where did I put this file? You can find it on modules. Yeah. So under modules, I included a section that says, like, if you guys can't ever find a file, I included a section that has like files, and it should say unit 7 packet with probability at the end of it, or prob. I think you guys can also find it in the modules section. Let me know if you can't find it. So here's a quick blurb of what we're going to move into, probability. And you are all familiar with this. You guys have done it before, and in the sense that this is the introduction. But this one kind of brings to light some of the extreme cases. So in an extreme case, you guys either have 0% chance that something happens or 100%. We're used to probability being tied to a percentage, but it's represented as a number, decimal number between 0 and 1, fractional value, where 0 represents 0 chances that something's going to happen. So in the event that a pregnant woman has a baby, here's a example. There's 100% probability, or p equals 1, in which the lady has a boy or a girl. No, that's arguable. I feel like nowadays, I think, you know, there's just being black or white about it. It's going to be a boy or it's going to be a girl. That's 100% probability. We're going to talk about that or situation a little bit more. What's the chances that that pregnant woman's going to have a zebra? 0% chance. So then that's the 2 extreme cases. Or, you know, we talk a lot about 50-50 chances. There's a 50-50 chance that the lady's going to have a boy or the lady's going to have a girl. And so when we study it, we're going to look at all the number of ways that an event can occur and divide it by the total number of outcomes. So what we're going to look at today is how to come up with these number of possible outcomes. And so when we talk about the outcomes, is it related to whether order matters or not? And so that's the difference between permutation and combination. So what I'd like us to do is just the shortcut that you guys learned from the other day, we're going to summarize right here. So the video that you're going to watch or that you have watched was on fundamental counting principle, and this idea of coming up with all the possible options when you're given a different number of ways of making a certain event happen. So for example, if decision M is like the example we used with sandwiches, was the number of ways that you guys, or the number of options for bread, and N represented the number of options for meat, then the total number or options of sandwiches made is just the product of the two. So if decision M can be made with M number of ways, and decision N can be made N number of ways, we saw that the shortcut was just simply to multiply the two together. So if you're in, and this applies to a lot of the options related to food. So ice cream shop offers a choice of 3 cone sizes, 15 flavors, and 8 toppings. How many cones are possible if you can only choose 1 flavor and 1 topping? So this is if you guys were going on, if you guys watched the video, there's the long way of doing it with the tree diagram and the table, but the fundamental counting principle allows us to come up with those number of choices by multiplying the different ways together to come up with all the possible options, which I believe in this case ends up being 360. Yeah. Okay, so that's a quick just summary of what you guys watched the video on. And then we're going to move past that to permutations, but let me give it a moment for people to copy that down if you're still writing that out. Oh, Cody, I'm going to post this video after I'm done with it. This particular periods on the agenda. Okay, guys, so if I can have you guys find page 6 for me. Okay, I want you guys to think of when you guys go up to a locker or have in the past gone to a locker. Does it matter the order in which you put the numbers? Like if your code is 12, 16, 4, does it matter what numbers go first? Yes, it does, right? And so there's a meme, I think, at the start of the next class where I say that combination locks should really be called permutation locks, because permutations are where order matters. So it's an arrangement of objects where order matters. So order or position matters. So if you're given situations, because that's what you guys have to do tonight, is determine between, like, is this going to be an example of permutation or combination? So think of the lock that you guys would have on a locker being a permutation locker because, or sorry, a permutation lock because the order of the numbers matter. So 1, 2, 3 is different from 3, 2, 1. And that's in direct contrast with combinations where 1, 2, 3 is the same thing as 3, 2, 1. It's just a grouping, combinations or groupings. And we'll go over the difference between those two as well. Okay, so we're gonna skip over this notation of factorial, but apparently you guys all learned factorials before. Do you guys all know what a factorial is or have heard of a factorial, like the exclamation mark in math? So we'll come back to that and why that becomes useful. How many of you guys know Mrs. Springer's daughter, Sierra Springer? I guess she's a year older than you guys. If you're a freshman or a sophomore, she's the same grade as you. Yeah, so she's on the swim team. I think I saw her on, not the news, but like some announcement recently where she won something for swim, like one of the relays. And so this is Mrs. Springer had written this this notes page, and so she's talking about her daughter here. So in Sierra's summer swim league, there are 6 swimmers in each heat, and every swimmer in each heat gets a ribbon. How many different ways can 6 swimmers finish in 1st through 6th place in their heat? So here's one hint I'm going to give to you guys, but it has something to do with lining up order matters. If it has anything to do with like you're placing in a like awards, like first, second, third place. So it's going to make a whole lot of difference whether someone wins first place or third place. So order matters for that. So this is an example of a permutation, and then I'll come back to the factorial discussion with this. But let's say you had to select from 6 swimmers for first place. So the first number of options is there's 6 possible people to pick from for first place. Now, if I selected Sierra to win first place, now how many people are left to choose from for second place? Okay, so there's now only 5 people left, right? So only 5 people left. And so now first and second place are filled up with two distinct people, 2 different people. And then we continue on with third place, 4th, 5th, and 6th, with the 6th place only having 1 person left to be in last place. So this is a permutation in which you have 6 total people to pick from, and you have you're going to select it in in their awards being 1st through 6th. So all your larger subgroup is the same thing as your smaller subgroup. Okay, so this can be written as 6 with a capital P. So 6 is a subscript with the P to denote a permutation. And the 6 here is just to say that you selected 6 out of the 6. Okay, so this is another way or notation of writing it. And then 6 factorial. That factorial just means you take the number that is in front of the exclamation mark and you times it by a decreasing integer value all the way till 1. Okay, so 6 factorial. Now, on the calculator, if you guys had to do 100 factorial, it would mean you guys would sit there and do 100 times 99 times 98, so on and so forth. So if I can have you guys find your Desmos calculator, and Cody, this is assuming there's no tie, but that's a good question. So go to Desmos scientific calculator. And if you guys are on a Chromebook or a laptop and you have the exclamation mark right above 1, you can just use that symbol. Just do 6 and then exclamation mark. If you don't, like for mine, I'm not connected here. You guys can do 6, and then if you go to functions, there should be a factorial symbol right on the bottom right of that section in the middle. So 6 factorial is 720 different ways in which you can arrange the 6 players. So in theory, okay, so 6 factorial, we're going to go back and put 720 different ways for that arrangement to occur. Okay, but we know that not every contest is going to have like, you're going to have 6 swimmers with 6 winners. That's just probably not likely. So what happens when you're playing the Olympics, you have a larger group and then a subgroup that wins. Okay, so there are 8 swimmers in the finals for the Olympics. In how many ways can the 8 swimmers finish in 1st, 2nd, and 3rd place for Olympic gold, silver, and bronze? Okay, so first I'm going to work it out the same way that I did with you guys on the above problem. And then I'll talk about where the formula comes from and why the formula is what it is. So let's say you guys have 8 swimmers to pick from for first place. So in the first spot, there's 8 possible people, okay, to pick for first place. How many people are left to pick for second place? Okay, good. So if we already selected one for gold, then there's 7 people left. And then this is a smaller subgroup that wins, gold, silver, and bronze. So how many people left for bronze? Yes, so 6, right? So we end there. We don't, go all the way down to 5, the 5 factorial part. So this is 336. So how do we do this using the formula? So this is one way of looking at a permutation where you have a large group and then a subgroup within that. So the way that we write this notation wise is the 8 stands for the total number of people to select from. This P stands for permutation as opposed to combination. And then you have a smaller group you're picking from. So that's the R value. 8 is the N value. That's the variable that's tied to it. If you look at the formula right below that. And 3 is the subgroup. Okay, so let me just apply the formula and show you guys how that makes sense with what we just did. Okay, according to the formula right here, you're gonna put the total number of people on top, factorial. So 8 factorial on top. We're gonna divide by the difference between N minus R. So in this case, 8 minus 3 factorial. It's in parentheses, so we would do the 8 minus 3 first. So that's 8 factorial over 5 factorial. Okay, why does this make sense with the problem we just did? So let's say you had 8 factorial, 8 times 7 times 6. Can I have you guys expand that out? My last class, or I think period 4, had a hard time seeing this, so I just want to show you guys what is why this formula is true. So you notice that the 8 times 7 is 6 is actually the answer to the problem. Okay, the 5 factorial part is the part we don't need, right? So we need to cancel it out somehow. So at the bottom, you have 5 times 4 times 3 times 2 times 1. And since those are factors, those will cancel out. And we do something similar to this in AP Calc with the factorials on a really difficult chapter for series, in which you guys recognize like 5 factorial on top, 5 factorial at the bottom will cancel out. And all you're left with is 8 times 7 times 6, which is the answer. So that's what the permutation does, is if you have a larger subgroup and then a smaller subgroup to pick from. Sorry, a larger group and then a smaller subgroup. Okay, so the situations that I just gave you are dealing with people. And we call, each person is its own person. And another word for that is distinct. So I know in the context of this, they're gonna say objects, but objects or people, they're distinct in the sense that they're different to choose from. So the question becomes like, what if you had a group in which some of the objects were non-distinct, that they're repeating? Down below here, we're going to talk about the letters A, B, and C. Okay, so rather than people, we're going to talk about objects. Okay, so how many ways can you order the letters A, B, C? Actually, maybe I'll have you guys start with just coming up with what you think the answer is for that. Okay, so there's 3 letters to choose from. Keep going and see if you guys can come up with what you think the answer is. Kind of like the 3 people. Okay, yeah, so most of you guys have the right answer. It should be 3 letters, then 2 letters, then 1 letter to pick from in that spot. So 3 factorial. In the formula itself, it would be 3, and then we're picking 3 letters from a group of 3. So how does that work with the formula? It would be 3 factorial over 3 minus 3 factorial. And that gets you guys 3 factorial divided by 0 factorial. 0 factorial must therefore be what in order for this to work? What do you guys think 0 factorial is equal to? Yeah, and the reasoning for this, it can't be 0 because you guys can't divide by a 0. So this must be equal to 1. 0 factorial is the number of ways you guys can arrange 0 objects, which is just, there's only one way to do that. Okay, so if you have no objects, there's only one way to arrange the no objects. It's kind of silly, but we eventually, when we move on to higher level math, this has to be true, just like for this permutation formula, it has to be true that that's 1 there. Okay, so 3 factorial, and then I want you guys to actually list out, like, what does this all mean? So the 6 means that like there's 6 different ways that you guys can arrange the letters A, B, C. Go ahead and see if you guys can come up with the 6 different ways. And I want to show you guys the distinction between that and then the next example. So just list out as many as you guys can, and then just see what it is that you end up missing. Okay, so the answer choices are there. If these, I'm gonna end up using this example to explain the combination formula for you guys as well. But I want you guys to take a look at the list that you guys came up with. If these people, if this represented an arrangement, which is what a permutation is of people, then the order in which the letters show up are matter, so that the ABC is different from ACB. But let's say this represents a grouping. For combinations, it's a grouping of people. So it's like these three people were selected to come along with me to the movies. Does it matter the order in which I selected my three friends, right? Like I should pick this friend first, then this friend, then this friend? Or does it really just matter what the group is? And if the order doesn't matter, and if it's just the group of like the three people that come as is still ABC, then we would consider all of this just one combination. Okay, whereas permutations, all of those are different because the order changes the arrangement of the list of possible choices there. Whereas a combination, the order doesn't matter. So all of this is just one grouping of three distinct objects. Okay, so we'll come back to that discussion and how that formula comes into play. So you'll see that this is really 6 of the same thing. Okay, so now when I talk about the letters mom, if this was distinct, and I'll write that word up there for here, distinct means that each one of the letters are different. Would you guys consider the letters that form the word mom distinct or not? This non-distinct? Okay, non-distinct in the sense that the M is not distinct, it's repeated. Okay, so if you guys have any repetition of letters, it's non-distinct. So here's what I want us to do is come up with the different ways first before we come up with the math behind it. So let's say I arrange the letters. I have MOM. Okay, and then here's my question to you guys. If I switch the last letter with the first letter, do I come up with a different word or is it still the same word? Yes, it's, wait. Someone said different, but if you switch the first M and the second M, you're still gonna spell mom. Okay, so that was different when we saw it with distinct letters. If I switched first and last, it was different. Okay, so that's the same. So in theory, how many possible, yeah, same word. How many possibilities are there here? What do you guys think? Yeah, good. There's 3 possibilities because switching the M's on here on the second arrangement and on the third arrangement is going to result in the same word still. So there's only 3 possibilities. So the way that we come about this is that, let's say initially there was 3 letters that we could pick from. So we're still going to have the 3 factorial on the top to say that it's 6 possibilities if the letters were distinct. But if there's any type of repetition, what we're going to do is to account for the fact that there's repetition, we're going to count the letter, we're going to find the letter that's being repeated or the object that's being repeated, and then count how many times it's being repeated. How many times is the letter M being repeated? 2 times. So we're going to divide by 2 factorial. So this can happen in longer words where there's more than one letter, and we just continually divide by the number of times that letter is being repeated. So in this case, we have 3 times 2 times 1 on top, 6, 2 times 1 on the bottom. Do we get to the same conclusion? Yes, there's 3 possible choices. Okay, so the formula for this when there's non-distinct objects is you do a permutation and factorial, but you divide by how many times each object is being repeated. So R1 in this case was the number of times M was being repeated, so 2 factorial. But if there's other objects or letters that's being repeated, we continue to multiply by that object that's being repeated. So I just put R sub 2, sorry, that's R sub 3. And then so on and so forth. So by however many letters or objects are being repeated and how many times they're being repeated. So let's try this one out. Let's say the word is longer. This time we're gonna see how many ways we can order the letters and rearrange. Okay, what number would go on top? Go ahead and type that into the chat. What number would go on top? What factorial would go on top? So you guys count how many letters there are in the word rearrange. So n stands for total number, 9 factorial. Then we're going to divide by however many times each letter is repeating. So someone give me a letter and how many times it's repeating. Okay, there's 3 R's, so you guys would multiply or divide by 3 factorial. Okay, the first, that 3 is for the 3 R's. Then what else? Yes. Okay, there's 2 E's, so times 2 factorial. And then there's 2 A's, so times another 2 factorial. We would continue this trend of dividing out to get rid of the repetition here. And so let's do that on the calculator. So it's 9 factorial divided by 3 factorial times 2 factorial times 2 factorial. Go ahead and see if you guys can do that on Desmos. So go to Desmos. Annika, you have a scientific calculator. Were you able to find the factorial button? What was that? Uh-huh. You can't find it. Is there, let me take a look at it. So for the Desmos, you guys, you just do 9 factorial. And then if you want a fraction symbol, you just do divided by, and it should put you automatically under. And then 3 factorial times 2 factorial, whether or not you guys do times 2 factorial or just times 2, that's fine because 2 factorial is just 2. Is there, yeah, so 15,120. Is there like a, what was that button called? Prob? PRB. If you guys are using a scientific calculator, it might be under PRB. Whoops, I think I just typed that to Mia. So just if you're using your own scientific calculator, look for a button that says PRB. There should be a exclamation mark or factorial button there. Okay, 15,120. Okay, can I have you guys go ahead and do Mrs. Springer's name? See what you guys get. Go ahead and fully do the problem. Okay, guys, that is the official answer, 3,326,400. Just double check that you guys had 11 factorial above in your calculation of 3 factorial times 2 factorial. The 3 is for the repetition of the r's, the number of times it was repeated, and s was the number of times or 2 was the number of times s was repeated. Okay, so our last bit of topic before I have us move on is what a combination is. So I'm just going to reference this example because it does display it nicely. So let's say I asked how many possible groupings of ABC is there, and order doesn't matter. Okay, how many groups of ABC is there? You guys would say that, well, there's only one possible group, because this is, if the order didn't matter, all of these are the same. So for example, let's say your friends are A and your friends are B and your friend is named C. Okay, and I said, and your mom said, you guys can pick 3 friends, but you only have 3 friends to pick from to go to the movies with you. So how many possible groups could you form with just 3 friends that you can pick from if your mom says you can only have 3 friends? So it's kind of an odd question, but if the order didn't matter, if it wasn't like A was my best friend, B is my second best friend, and C is my third best friend, it's just whoever I pick gets to go to the movies with me. There's only really one possible group that can account. Like all of these order doesn't matter. So on a combination, the answer to this, what's the combination of A, B, and C? What possible groupings are there? There's only one. Okay, so what we do is we do the permutation calculation, but we divide out the number of ways in which it could repeat. So for this particular problem, we would have to divide out the 3 factorial. So going back to our, I believe it's back 1 page, we're just going to do one additional example here on combinations, and then I'll show you guys how to do it on the calculator. So a combination is a group of objects. So rather than an arrangement of objects, it's a group. And grouping doesn't matter on the order. So let's put order doesn't matter. A group of objects in which order doesn't matter. It doesn't matter if I pick friend A first, friend B, or friend C. It's just if I only have 3 friends to pick from and I can take 3 friends, that's one possible grouping. So the way that we account for this is you're going to think of it as the normal permutation formula, but we just divide out the number of ways that it can be repeated. So I'm just going to write it the way that you oftentimes will see, which is r factorial and then n minus r factorial. So let me circle one part of it. This is the permutation formula over here, n factorial divided by n minus r factorial. For our purposes, though, we wanted to basically divide out the number of ways in which that group can repeat itself. If order didn't matter, this is that r factorial that we would have to divide out by. So for that example we just did, it was 3 factorial divided by 3 minus 3 factorial is the permutation part of it. And then that the 3 groups that could get repeated if the order did matter, this is what we're dividing out here. And so what we're going to do is let's look at a specific example. You're going to know it's a combination if you're like, okay, well, it doesn't matter who I pick first. And if it's a group. Okay, so Natalie has 16 close friends. How many ways can she choose 5 to be her bridesmaid? So the 16 is going to be the total number, just like with permutations. And 5 is going to be the subgroup or your R value. So we would write this notation would be 16, and we would say the C would be choose. Okay, so think of it choosing a group. So of the 16 people, we get to choose 5. So we say 16 choose 5. And it's actually really simple, the formula. You would just do 16 factorial. Doesn't matter which one you do first, whether you put the 5 factorial first or the difference between 16 minus 5. But one of them is the R value, and the other one is the difference between N and R. So 16 minus 5 factorial. And the nice thing is your calculator does the calculation for you. But if you were to simplify this, if you wanted to do it without the calculator doing the work, you would do 16 factorial divided by 5 factorial times 11 factorial. Okay, so the 16, this part of it is what you guys would have gotten had you guys done the permutation and order matters. Dividing by the 5 factorial gets divides out the number of ways in which that 5 people can, or the arrangements can be repeated. Okay, so what I'd like you guys to do is follow me on this calculator stuff, and then if you have a scientific calculator, it's on your scientific calculator under PRB, but we're going to do 16 choose 5. in one simple step. Okay, so go to your scientific calculator. Rather than doing a calculation like this, if it's a combination or permutation, you guys can simply go to function. So if you're on your calculator, hit PRB, and then do n choose r down below there, right next to the factorial. You guys have that combination. And within that, you guys are going to put n, which is your large group, and then comma your subgroup. Was it 5? Okay, so 16 choose 5. That's how you guys would enter it on the calculator. And it does all the factorial calculations for you. So 4,368. On your calculators, let me know if you guys can figure it out or if you need help with it. It might be a little bit different on the syntax. Oops. Okay, it helps for you guys to go through these together. Like, is it permutation or combination? So with the time left, yeah. Let me show the calculator again. So clear, you're gonna go to function and then hit the n choose r. There's also one for permutation as well. And then enter in the large group, comma, n, comma, r. Let me know if that makes sense. Okay. You're good, Mia? Okay. All right, you guys. So on your homework assignment